It's cold.
Whenever you're dealing with extreme temperatures, you need to be prepared and bring the right gear. The weather doesn't care if your fingers are too cold to press your valves down or what temperature your iPad overheats at. Unfortunately, most musicians don't really have a choice when it comes to their instrument, as I don't think many instrument manufacturers are specifically engineering trombones to perform well in sub-zero temperatures. The biggest issue we have to worry about with temperature is pitch. If the temperature is warmer, your instrument's pitch will tend sharp, and if it's colder, it'll tend flat. But why is that? Well, pitch, or frequency, is proportional to the speed of sound, and that speed is proportional to the square of the pressure of the air that sound is moving through. So, using the dreaded ideal gas law from our high school physics class, we can see that temperature is also proportional to pressure. So, if temperature goes down, so does pressure, making the speed of sound slower, and finally making the pitch go flat. Alright, I'm doing the rest of this inside. You've probably seen on camping equipment, such as sleeping bags and sleeping mats, a temperature grading which tells you in what conditions your gear is most appropriate. Today, I want to do that for my trombone. But what does that even mean? Well, I intend to find out the highest and the lowest air temperatures in which my trombone is still capable of playing at standard concert tuning, or tuning A to 440 Hz. To account for performing under various conditions, including temperature, nearly every musical instrument has some sort of mechanism that finally adjusts the tuning of the instrument to fix any small deviations from the ensemble. On the trombone, I have this tuning slide here, which I can push in, which I can push in to make my pitch go sharp, and pull out to make my pitch go flat. Since the temperature also makes my pitch go sharp and flat, my end goal is to find the coldest temperature that makes my trombone just flat enough where pushing my tuning slide all the way in brings me back to concert pitch. And likewise, the warmest temperature that perfectly cancels out the effect of pulling my slide out as far as it goes. Now, a couple of things make this experiment incredibly impractical. Even in cold weather, your breath going through your instrument is going to warm up the air inside your instrument, meaning the air your sound is actually traveling through is effectively warmer than the outside temperature. Also, the most important thing with an ensemble performance is intonation with the other members of your group, and not tuning to some abstract universal standard like A440. However, for the sake of the physics demonstration, and so that I have at least one constant to help me solve for a plethora of unknowns, I'm gonna do it anyway. This next part is gonna get a little mathy, so just hang in there with me. I promise everything is gonna simplify quite nicely. Let's pull up some of those physics formulas again. We know that the fundamental frequency of a length of pipe is equal to the speed of sound divided by the wavelength, which is twice the length of the pipe. So if we use a fundamental frequency of B flat 1, which is about 58.27 Hertz, and assuming the speed of sound is 343 meters per second, we should get an effective pipe length of about 2.94 meters, or 9 feet 8 inches. However, there's one more physical phenomenon which throws this length out of whack just a bit: end correction. End correction is a short length that's added to your actual length of pipe in order to calculate the precise resonant frequency. What this means in effect is that the wavelength of our sound wave is actually slightly longer than twice the length of our pipe, with one end precisely at the mouthpiece and the other end out some distance past the bell, not right at the bell. You can calculate the end correction by multiplying the diameter of your pipe by some coefficient, but I could just get this experimentally too. If I know that my trombone should be 2.94 meters, and then I measure its length when it's precisely in tune, I can find the difference between my calculated value and the expected value. That's the end correction. Let me just pause here for a second and say that I'm making a ton of simplifications for this video. The coefficient of end correction is not as constant as I make it seem, and it can change due to a wide variety of factors, such as pressure or even temperature itself. Additionally, the metal in the brass instrument is going to expand or contract, whether it gets warmer or colder, making the length of the tube change with the temperature as well. Also, there's a huge flare at the end of the brass instrument. It's not a perfectly cylindrical tube, and some brass instruments are even conical all the way down, so it's not going to function exactly like a perfectly ideal open-ended tube. The acoustical physics of musical instruments is immensely complicated, and I'm here just working with a handful of extremely generalized high school physics equations. Instrument manufacturers spend years studying and honing their craft so they can make instruments that both sound amazing and can play in tune. End correction especially is an incredibly complicated concept that I've barely scratched the surface of in this video. I'd highly recommend you doing your own research if you're interested. We don't really need to dive too deeply into all the physics equations from the beginning of the video. We just need to know that the speed of sound is proportional to the square root of the absolute temperature, and we can assume that none of the other variables, pressure, volume, etc., are going to change. I can use the temperature that's listed on my thermostat to more accurately calculate the speed of sound in my apartment right now. Okay, so the 343 meters per second assumption is for 20 degrees Celsius or 68 Fahrenheit, which is 293.15 Kelvin. I think it's a little bit warmer than that in here right now. So if I divide that out by the square root of 293.15, I can multiply back in the square root of the actual absolute temperature. For each degree Fahrenheit, I need to add 5/9 of a Kelvin. So let's see, it is, let's see that temperature. I promise I did not have that planned. Just a couple more steps. I need to move my tuning slide so my instrument is perfectly in tune here at 68 degrees. Then I need to measure the length of my tubing, where the tuning slide's at, then push it all the way in, measure that, pull it all the way out, measure that too. The end correction won't change, it's only dependent on the diameter of the bell, not the length of the tubing. Then I'll have 3 different tubing lengths, and I know the temperature for one of them, and all that'll be left is solving for the last 2. Let's do this. So my 3 measurements are 2.83 meters at the current room temperature, 2.81 meters with the tuning slide at its shortest, and 2.90 meters at its longest, giving me an end correction of about 0.11 meters. Since I know these lengths, I can rearrange the frequency equation to isolate the speed of sound. I know if I divide the speed of sound by the square root of 293.15 Kelvin, I'll have to multiply whatever's left by the square root of the true temperature to get the actual speed of sound. So if I isolate this and then square that, I'll get these temperatures, but they're in Kelvin. So I'll have to convert to Fahrenheit to get 61 degrees at the coldest and 94 degrees at the hottest. Well, that was rather underwhelming. So what can I actually do with this information? Will this prepare me more for performing in extreme environments? Will this help me be more in tune with my instrument's needs and desires? Does this have any practical applications, or was this just an excuse for me to do some math problems? I think the real takeaway from this video is it's kind of chilly out right now.